All right, so this day wasn't too hard. It was just a little bit of debugging and a little bit of having to think about how to approach it. Overall, the question was kind of fine. So here's how I approached it. I was pretty happy with my solution. So if you look at the kind of code, it's basically just telling you to simulate poker. The only real difference that I can tell, instead of having to break ties with a high pair, high card, you just go in order of the cards you have. So without any further ado, let's start coding it. All right, so in our main, let's go ahead and here. I'm actually going to go ahead and create a function called solve, and you'll see why in a little bit, but this is basically what we're going to be using. So solve input, and I'll return none for now. And just to kind of, I'll return like one, and then just to kind of like show that this is working, right here. So we have our reading our inputs. So what this solve function should do is just basically make a collection of hands from the inputs that we get, and then eventually somehow sort them, and then based on that, score them and return this answer. So first of all, to create this, let's go ahead and we'll create a class called hands, and we'll basically give it each line for line in input.split lines. And then for this, we're going to create a class hands. And this is basically going to, this class should give me basically like a representation of the hand that I can somehow compare and do all this stuff with. So inside of here, we'll create our init, self, align, and then for this, what we're going to do is first we'll split up the line. And the reason why we're doing this is we see an input in this kind of form where, first of all, we're getting passed on a line like this. The left side is going to be the actual cards we have, and the right side is going to be our bid. So we write down our bid like this. And first, let's save that bid actually to a variable like that we can use later. So we have it like this. And then now let's go ahead and parse all of our cards. So we'll do cards equal to a tuple, and tuple is so that we can compare this later. And I'm going to create a function called translate. And what this should do for C in raw, this translate function should basically go ahead and this translate function should go and turn the strings. Like for example, if I have a 3, it should turn into the number 3. If I have a t, it should turn into the number 10, and so forth. So we can do if c.is numeric, then we return int of c. So that's ints right out of the way. And then otherwise, we'll just go ahead and return, we'll create a dictionary. And then inside of here, we'll do stuff like if t is equal to 10, we'll return that. If it's equal to j, we return 11. If it's equal to queen, we return 12. King, 13. And then ace, which is the highest, we'll just set 14. And then finally, since this is a dictionary, we can just index into it with whatever a c is and return this. So now we're translating all of our things fine. And to make our lives a little bit easier, let's just make a representation function. And for now, we'll just return self.cards as a string. So now if I go ahead and just print out hands, boom. So we're now reading all of our inputs on like this. And if you can see, so the first input that we have is this 3, 2, T, 3K. You get 3, 2, 10, 3, and then king. So this looks good. All right, so the next thing we need to do is we need to figure out what kind of type this has. So the types are in this order. We have 5 of kind, 4 of kind, full house, 3 of kind, 2 pair, 1 pair, and high card. So let's go ahead and create this new function. So I'm going to do self.type is equal to self.getType, just to kind of make this nice and organized. So now we'll create the function def get type. Also, if it's not clear and like obvious, I've already written this code. I just finished it and I have it open on a second monitor. This isn't normally how I would go around writing everything, but this is just kind of like a very polished version of how I would do it. So the thing we're going to use here is we're going to use a counter object. And here, let me explain this in a second. Let me just get down this code. First of all, we're going to need to import this. So from collections, import counter. This is something that basically comes with all Python. You don't need to install this as a separate package, but you do have to import it. And collections is here. It is a very, very useful set of these objects. And the big one that we're going to be using today is counter. Counter, I can basically give it some kind of iterable object and it'll automatically count them for me and I can use it just like a dictionary. So here, we're going to be using in this case because I'm going to be counting the cards that I have. And then we're going to do highest is equal to max counter.values. So basically what this is going to do is it's going to count up all of the cards that I have, and then Here, for now, let me just return 0. So everything's the lowest power, and I'll just print out what my counter is. Oh, so this is day 6. Here. So you can see, for example, for the first one, where we have 2 3s, a 2, 10, and 13, we have 2 3s, 1, 2, 1, 10, 1, 13, and so forth. And so from this, we can kind of make all of our logical deductions about how we're going to score our cards. And the way that I'm going to do this is get type is going to be an integer where the higher it is, the more powerful it is. So if we go ahead and count out how many we have 0, 1, 2, 3, 4, 5, 6. So 6 should be the most powerful type. So to do this, we'll do if highest is equal to 5, then we return 6, which is a 5 of a kind. And so this is basically saying if the highest number of a card that we have is we have 5 instances, we know we have a full house. Then elif highest is equal to 4. So if we have 4, then we know we have a 4 of a kind. 4 of a kind. And then now's here we get a little bit kind of fancy with our logic. So counter is basically going to tell us stuff like this. If you notice here, we only have 3 elements in our counter. That's because if we look at the one this corresponds to, here we have a 2 pair, a 2 pair, and then 1 card left over. If we have a full house, that means, first of all, like we have a 3 pair and a 2 pair. But the cool thing is we would have 2 unique cards. So if I check the length of counter, and if this is equal to 2, then I know that this is going to be a full house. The only other case this could be is if we had 4 of one card and then 1 of the other, but then that would already return here because it's a 4 pair. So now we've got full house covered. Now we'll do elif highest is equal to 3, and this is going to be 3. This is 3 of a kind. And then otherwise, so if we have a 2 pair, then our counter would have 3 objects. Because if you look at, for example, for this one, we have 3 objects because we have 1 for 1 pair, 2 for the second pair, and 1 here. And the only other case there could be is if we had 3 of one card and 2 different cards, but that would already be caught by this, so we're fine. So we'll return 2 for 2 pair, and then elif highest is equal to 2, then we have 1 pair, 1 pair, and otherwise we have 0, and this is a high card. So now we did nothing else in our code, but what this is now doing is it is scoring all of our cards. And then now I'm going to do a nice little fancy thing I can do in Python by just sorting this list. But if I sort this, how is it going to sort our own custom objects? If I call this, we can see we get an error where less than is not supported between instances of hand and hand. And if I show the full error statement, we can see it complains when I try to sort it. The way sorting works in Python and most languages is you only need to overload the less than operator. And based on that, it'll do all of the other logic for you. So if I just set it back to this test, let's go ahead and define that less than operator. So we can do that by doing def lt for less than. It takes in self and it takes in some other object. So how can we compare so we basically want to return true if this this object, is less than or worse than the other card or the other hand. So the way we can do this is first of all, return if self.type. So if our type is weaker, because the numbers go higher the stronger it is, than the other type, then we have a less than hand. Or if we have the same type and our highest card is lower, and we have to go in order. So for example, if the first highest card is a tie, then we go here. If the first highest card is a tie, then we go to the next card. And we keep doing this until one card is less than that. And the reason why we originally chose these as tuples is tuples actually do this perfectly. If I'm comparing 2 tuples, it'll return basically less than if it'll check every element one by one until an element is either less than or greater than. If it's equal to each other, it goes to the next element, which is what we want. So I can just go ahead and do self.cards is less than other.cards. Now if I run this, it automatically sorts our thing for us. And if we go ahead and look at what they tell us, when we end up sorting these things, we should get 765, 220, 28, all this. So I'm going to go ahead and in our string, I'm going to also print out I'll put it in little square brackets like this, but I'm going to print out its bid, self.bid. I'll change this into a string. So here we can see we get 765. Oh, here, sorry. This was the code that I changed. We get 765, 220, 28, 684, 483. If I look here, 765, 220, 28, 684, 483. So we're sorting it perfectly. So now to go and actually score it, we'll have our answer is equal to 0. And for I, and then hand and enumerate hands, because I want to get the index and the value itself. Answer plus equals, so I is 0 index, so we'll do I plus 1 times hand.bid. And then finally, we'll just return answer. So let's see what we get on the test case. 6440. If I look here, we get 6440. So now, if I run it on my actual test case, I can see I get this value. And if I go ahead and submit this answer, we get it right. Perfect. So now part 2. So for part 2, if we look at what they're telling us to do, is J's now become wildcards. So they inherently are now lowest value, but at the same time, they can be filled in to do whatever they need to make your best hand. So to program this actually ends up being nice with this implementation. Let's go ahead and just kind of do this in order. First, to translate it, J's now need to be the weakest card. So we'll add a new parameter. So part 1 as a Boolean. And then now, so J will be 11 if part 1 is true. Otherwise, it'll be equal to the value of 1, which is the lowest value. The reason I'm choosing 1, I could choose anything lower, is because 2 is the other lowest value, and I just turn it as an integer. So we'll have J be 1. So now translate's taken care of, but hand also will need a part variable. So here, now, let's go ahead and add that in. And then we'll also just save it to self.part1. Or actually, no, let's not do that. Let's just pass in as an argument. So part 1. So now this is getting translated. And then here, the solve will also need a part 1. And just to make sure that I actually use this right, I'm just going to make it a mandatory argument. And this is only getting passed in here. So part 1. And then now, oh, and this should be false because now this one's not part 1. This one's true because this is part 1. All right, so now just to make sure that I haven't gone crazy, let's go ahead and just run this and make sure nothing goes wrong. All right, so something does go wrong. Let's look at where, oh, I need to specify here. It should also take in part 1. Cool. All right, so right now it's doing nothing fancy. That's because we haven't really done much with it. But now translate should be automatically changing our thing. So if I go ahead and print out my hand again, we should see anywhere where we saw an 11 should get changed to a 1, which is perfect because the jack is now worth 1. And that's because we added in this whole part 1. And this is a ternary statement where basically if this condition is true, we have this value. Otherwise, it uses this value. All right, so now the rest of the logic we need to change. So what we need to change is how we're kind of doing this get type here. So the way that I did this is I separated this and I kind of just tried to more or less hack this into my original solution. So if self.part1 is equal to false, then we're going to go ahead and we're going to save how many wildcards we have, which is the jacks. So this is how many how many ones are in the counter. And then we're going to get rid of this from the counter. And the reason why I want to get rid of this is because for stuff like this to work, I don't want the jacks to be counting anymore. Because if I have, let's say, a 2, a 2, a 3, a 3, and 1 jack, this counter will tell me there's 3 objects. But I should be able to make a full house by using the jack for one of the pairs. So we get rid of that from the counter. And then now we have our highest. And this is the variable we're using to see the highest pair that we have. And we're going to set it to the number of wildcards we have. And then normally, what I would do is highest plus equals max counter dot values. So we have it basically what it was originally. But the problem here is there is, at least in my input, there was a test case where I had all jacks as my input. And then this threw an error because counter was empty. So we'll do if counter. So to basically check if our counter is a valid counter, like there is something in it, then we'll go ahead and add all of this. And then finally, I believe the rest of this code should be the same. And so if I run the test case, let's see what I get. Oh, hand does no attribute part 1. That is because I should not have this as self. I should have this like this. All right, and we get the answer of 5905. And then here, if I run it on my actual test case, we get it correct. So let me go ahead and explain a little bit more about this part of the code. So when we have something that's like, for example, this line, so KTJJT. So we end up with a counter, and let me actually go ahead and just print out this data. Print counter. So the KTJJT is, I believe, this one. So this 13s are K, this ones are jacks, and this ones are T, or 10s. So for this line, what we're then doing to make it kind of massaged into the best wildcard possible is we're saving how many wildcards we have. So in this case, it would be 2. And then we delete those. So we end up with a counter that's just 2 10s and 1 king. And then our highest pair we can make is whatever we were best able to make with the current cards we have, and then add on every wild card we have. And that's just because the way these cards, the game is scored is that, if you can make a high number of pairs, that's always better than anything else. And then to kind of make sure that we're testing this full house and 2-pair fine, we're getting rid of this from the counter so that the number of unique elements is not influenced by this. Because, for example, for this KTJJT, we end up, I think, making this a full house. Oh no, we make this a 4 of a kind. But if we wanted to consider this a full house for some reason, we would basically see that we have a unique K and we have a unique T. And that means there's only 2 unique options. And so the jacks basically just get allocated wherever they need to make it a full house. But in practice, this makes a 4 pair. And the reason why is because if we take out our jacks, we end up with 2 wild cards, and then we have our best pair of 2, because we have 2 T's. And we just add this on to make it a 4 pair. And so all of this logic goes ahead, and I think I already showed this, but yep, passes. So yeah, if you have any questions, let me know. I think this day was a little bit tricky, but if you get the logic, then you're chilling. All right, good luck.